Alright guys, welcome to this page of the notes. What we're going to do is we're going to just continue this idea of using or solving logarithmic equations, and we're going to do it now for a couple of different word problems or sort of real world scenarios here. And the first one is actually one that's really near and dear to my heart. When I first started teaching, actually the first couple of classes I taught was a chemistry and an AP chemistry class. And so finding the pH of an acid or a base is actually something I've always really enjoyed doing. And now that I get a chance to show you how it works based on what we've learned about logarithms, I'm really excited about it. So keep in mind that when you're finding the pH, of a solution, what you're actually doing is measuring the hydrogen ion concentration in the solution. Picture this for me, if you real quick. If I've got a beaker and I have some liquid in that beaker, what I'm doing when I measure the pH, right, is I'm trying to figure out how many hydrogen ions, which are just free protons. Generally you write them as an H+, right? It's a hydrogen ion that's lost its only electron and you're left with just a proton, right? And what happens is if the concentration of hydrogen ions is really high, you'll have something that's really acidic, right? It's got a lot of just free protons running around. It's super acidic. It'll have a real low pH, right? 1, 2, 3, those are your strong acids. They have a really high hydrogen ion concentration. Generally though, if you've got a good chemistry teacher, they'll tell you there's no such thing as just a free proton running around. Almost always those guys will immediately connect themselves to a water and you'll wind up with the hydronium ion H3O plus. And that's what it'll actually look like in solution. But no big deal whether you do H plus or the hydronium ion H3O plus, whatever. If you've got a lot of these guys, the more of them there are, the more acidic the solution is going to be. On the other side, if you have a solution that has lost those hydronium ions, if you've lost those H pluses, what you actually wind up with then in solution are the hydroxide ion, OH minus. It's a water molecule that has lost a hydrogen, and so it has a negative on it. And the more hydroxide ions you have, the more basic the solution will be, right? So the more of these guys you've got running around in solution, the more basic you'll be, which is the opposite end of the pH scale, where you have pHs of 10, 11, or 12, right? Real sort of basic solutions. So what we're going to do here in this problem is we're going to use, generally what'll happen is when you're doing these problems in chemistry, you'll know the hydronium or the hydroxide ion concentration. It'll be some really big number, right? So remember what we said we generally like to do when dealing with really large numbers or really small numbers is we convert it to a logarithmic scale because that makes it a much more manageable number. Consider this. I've got this graph. I'll graph a logarithm for you. Let's say it looks like this. There's my vertical asymptote right there. Okay, so here's what happens. Let's say that I have a really small number. Let's head toward negative infinity, right? Well, dealing with really small numbers in scientific notation can sometimes become cumbersome, leads to errors, losing numbers, forgetting numbers. Generally just scientific numbers and scientific notation kind of freak kids out, especially in chemistry. So what we'll do, right, I showed you this back when we were graphing logarithms, is we convert that really small number to a logarithm, which is going to wind up being a much nicer number on the y-axis, right? So you may have something that's really small, like say times 10 to the negative 5th, or times 10 to the negative 6th. But when you convert it to a logarithmic scale, it comes out to be 3 point something or 4 point something, which is a much nicer number, right? So that's what you would generally be doing. However, in this particular example problem, I've given you the pH, and I'm asking you to find out what is the concentration of the hydrogen ion in the solution. So let's go ahead and look at the problem. The pH of a substance is defined as the concentration of the hydrogen ions, H+, in moles. We are given the formula for calculating pH. If you've had chemistry, you'll recognize that formula. If you haven't gotten to acids and bases yet, spoiler alert, I don't mean to steal your teacher's thunder, but this is how you're going to go back and forth between pH and hydrogen ion concentration. Now, what I want you to do is find the amount of hydrogen ion in a liter of acid rain if the pH is 4.2. Decently acidic, not super acidic, but decently acidic. So here we go. I know that my formula is pH is equal to the negative log base 10. So actually I won't even write it because we know that base 10 is implied. What this means is you'll be able to use the log button on your calculator, if I even need to use the log button. And the pH is 4.2. Well, there's the pH. So go ahead and plug it in. What I need to do is I need to solve for H+. So the first thing I'm going to need to do, right, to get this H+ by itself, that minus sign has got to go. I'll move it to the other side. Negative 4.2 is equal to the log of the hydronium ion concentration, the hydrogen ion concentration. And now, guys, it's Snail Method. At least, hopefully, you should right away recognize it as the Snail Method. So our good old trusty Snail Method even shows up in chemistry. Remember, it's a base 10. We don't have to write it, but it's implied. You always start with the base. So I'm going to have a base 10. And then I work my way around the equal sign. So negative 4.2. So 10 to the negative 4.2. Work my way back around is going to be equal to the hydronium ion concentration. Again, in chemistry, the brackets mean moles. So here we go. 10 to the negative 4.2. You just go ahead and throw that into your calculator, and you wind up with the hydrogen ion concentration is equal to 6.31 times 10 to the negative fifth. I'm going to write moles because we like numbers with units, but just remember the brackets mean moles in chemistry. And again, here's what you're doing in chemistry, right? I could have you go either way. If I give you a pH, you can now calculate the concentration of the hydrogen ion in solution, right? This is how many hydrogen ions I've got running around in the solution, which when you stick that litmus paper in there and it turns that nice shade of reds, pinks, and yellows for acids, right? 4.2, it's because I got hydrogen ions running around in there. Or we could go the other way, right? If I give you the concentration of hydrogen ions, this kind of ugly number that kind of freaks kids out, we could plug this in right here for H. You take the negative log of that concentration, we convert it to a log scale, and you would get yourself that real nice number, 4.2, right? This is much nicer to work with, much nicer to think about than this number in scientific notation, which I explained to you is why we like converting to logarithmic scales. It takes a number that's kind of scary and not so nice and converts it to something that's really pretty easy to work with, 4.2. All right, so just keep that in mind when you guys get to chemistry and you're into the acids and bases, right? It's a log. The pH scale is a logarithmic scale. You're just simply taking concentrations, converting them to logarithms, and getting back nice, neat numbers. All right, guys, head on over to the next page of the notes. We'll take a look at another example problem. I'll meet you guys there.